My Next Forum presents a study on mining AI trends and workforce transformation.
The global transition to a low-carbon economy demands a massive influx of critical metals like lithium, cobalt, and copper. Yet, over the past 2 decades, the average grade of active ore deposits has plummeted by nearly 30%. For greenfield exploration in untouched areas, the probability of commercial success without advanced predictive analytics has fallen to a range of just 0.3 to 0.5%. This chart shows the divergence between physical ore grades and technological investment. As ore quality declines, financial growth projections for AI applications climb, jumping from roughly $29 billion in 2024 to over $478 billion by 2032, a compound annual growth rate of 42%. As traditional extraction hits a ceiling of diminishing returns, the ability to interpret complex geological data with speed and precision has become a primary differentiator for commercial success. Most modern mines operate in extreme geographic isolation, where relying on standard cloud computing channels introduces severe latency problems. Transmitting data to a centralized cloud AI takes up to 500 milliseconds, an unacceptable delay for safety systems operating heavy machinery, which require reaction times in fractions of a millisecond. To solve this, edge computing relocates critical data processing directly onto the machinery's onboard computers. Achieving this sub-millisecond latency at the edge is the technical prerequisite that makes autonomous heavy industry possible. A modern terraced extraction site is a complex environment, operating on a scale that dwarfs traditional heavy machinery. To navigate this environment, thousands of autonomous haul trucks are currently deployed globally, operating entirely without human drivers in the cab. Software-defined autonomy platforms continuously calculate precise travel routes for these vehicles. This optimization reduces overall fuel consumption by 10 to 15% and minimizes wear on large-diameter tires. In underground operations, standard GPS signals fail completely. To compensate, AI systems rely on simultaneous localization and mapping, or SLAM technology. Using LiDAR sensors to constantly scan and map their surroundings, autonomous drilling rigs and loaders navigate and operate in high-hazard, off-grid zones. The human workforce is relocated from the physical rock face to remote digital operation centers located hundreds of kilometers away. Removing human bodies from the blast zone changes the risk profile of the mine, allowing equipment to run continuously without the interruptions inherent to manual labor. The viability of this architecture is evident in Kazakhstan, where a national strategy for digital development supports Eurasian Resources Group's deployment at the Vostochny open pit. Running on a private 5G network, a fleet of driverless trucks has successfully transported over 2 million tons of rock in commercial operation. By implementing proprietary digital tools and full-scale 3D digital twins, the enterprise generated an economic effect exceeding $111 million in a single year. Coupling state-backed telecommunications infrastructure with localized edge AI demonstrates commercial scale and viability outside of traditional Western markets. The extracted material then reaches the mineral processing plant. This is a system with hundreds of variables, requiring real-time adjustments for changes in incoming ore hardness and particle size. High-speed conveyor belts are equipped with hyperspectral cameras. Neural networks analyze the spectral characteristics of the material to execute intelligent optical ore sorting. These algorithms identify and reject waste rock on the belt before it enters the energy-intensive crushing stage. Further down the line in flotation cells, computer vision analyzes the color, size, and speed of froth bubbles to regulate the consumption of chemical reagents. Optimizing the process to increase the final recovery rate of valuable components by even 0.5% generates millions of dollars in additional profit, all while minimizing the facility's environmental footprint. In regions like the European Union, regulatory frameworks prioritize environmental sustainability and demand deep geosphere data analytics. Mining operations deploy distributed wireless sensor networks, like InfraGard, to record microscopic ground movements in open-pit slopes and along the dams of tailings facilities. Edge systems process this data locally to filter out environmental noise, providing accurate early warnings of landslide risks and structural breaches. Underground, advanced deformation sensors calculate rock convergence, predicting roof collapses before any visual signs appear to human inspectors. Transparent, verifiable AI monitoring has become a requirement for proving ESG compliance and securing institutional investment. By eliminating micro downtime from shift changes and meal breaks, companies begin shifting costs from operational payroll to capital investments in technology. At traditional mines, human labor accounts for up to 40% of operating costs. By 2031, that payroll burden is projected to drop to roughly 20%. Financial departments use this automation efficiency formula to balance human labor costs against AI infrastructure. It weighs the total cost of a human worker against the falling cost of hardware, software licenses, and human experts required to verify AI decisions. This financial restructuring reduces the all-in sustaining costs per ton by an average of 15 to 22%, protecting margins even when processing low-grade ores. The physical deployment of these systems is constrained by a fragmented global regulatory landscape that dictates how industrial algorithms can operate. The European Union enforces a compliance model that legally classifies AI systems used for personnel management or safety tracking as high risk. In the United States, directives categorize connected mining machinery as critical information infrastructure, making it a target for cyber attacks. China operates on a model of state control, mandating the use of domestic machine learning libraries and prohibiting foreign algorithms within strategic enterprises. Because industrial software cannot cross borders freely, international mining operations are adopting localized, sovereign technology stacks managed by specialized compliance engineers. This technological pivot drives a mechanism called skill compression, where multimodal AI assistants reduce the time required to complete complex engineering tasks. AI closes the capability gap between junior staff and experts, neutralizing the talent premium companies are forced to pay in an overheated labor market. By 2031, legacy manual professions like ground-based mine surveyors, open-pit drillers, and cartographic technicians will see a significant decline in headcount. They are being replaced by a new class of digital operators. Mines now require data geologists, edge AI engineers, and autonomous systems controllers. These roles demand a T-shaped competency matrix, broad digital literacy across the top, supported by deep geological expertise down the vertical axis. This budget for retraining addresses the final bottleneck, the ability of the remaining human capital to audit and verify the decisions of the AI systems they manage. In this high-stakes environment, winners are defined by the synergy between advanced algorithms and human expert experience.